1,000 years from now, you could create robots that could go into space and could carry on your civilization, not with you as individuals, but at least your technology, your culture in a sense. Is
AI could continue.
Yeah, exactly.
Yeah.
But we probably would have seen that too. So that tells you again that lifetime of intelligent civilizations probably isn't very long.
My name is Nick Nagaka and you are locked into Culture TV. For the culture, by the culture. Let's go.
Chris, thank you so much for coming down today, mate.
Sure, my pleasure.
Yeah, let's jump straight into this. So, for the viewers and listeners who don't know a bit, your background, can you just give me a quick summary on your background, please?
I'm from the United States, and I did my education there, but I've been in the UK now for about 15 years.
Yeah.
And I am an astronomer, and my degrees are in physics and astronomy.
Yeah.
And I worked at various places, including California Institute of Technology, University of Nottingham, and now I'm at the University of Manchester, where I'm a professor.
Why did you pick Manchester to come to?
Well, Manchester is really one of the big centers for astronomy in the whole world.
Oh, really?
Yeah, it is. We run some of the biggest radio telescopes, and we're the headquarters for the next generation big radio telescope called the Square Kilometer Array.
Yeah.
Also abbreviated as SKA.
Yeah.
And that's a Jodrell bank.
Yeah.
And which is not too far from here.
Yeah, Jodrell bank. And
it's a really good place to do astronomy, and it's Manchester, which is a city I've always liked to.
Yeah, it's one of the cool spots, isn't it, Manchester?
Yeah, I think so.
How long have you been here?
Only about a year.
Just a year?
Yeah.
So you're getting used to it. And how long were you in Nottingham before that?
I was in Nottingham for about 15 years.
15 years?
Yeah.
Your accent's not faded in the slightest, has it?
No.
How often do you go back to the States?
Well, before the pandemic, I would go back a couple times a year, but I haven't been back now in almost 2 years.
Really?
Yeah.
Shit.
Yeah.
You're looking to get back after... Is it November they're changing the rules, isn't it? So you can...
Well, as an American citizen, I can go back.
Oh, you can go back anytime?
Yeah.
Oh, okay.
It's only people who aren't citizens.
Right, okay. Yeah. Right, yeah. So, tell me about this new telescope that they're launching. It's the SK8. SK8.
8A.
Oh, is it A? SK and the letter
SKA.
A. Okay. What's different about this telescope?
Well, it's very large and has a very large collecting area, which means that it can see things that we can't see now.
Right.
So it'll be able to do things that we can't do. It'll be able to detect signals that we can't detect. It'll be able to see pulsars and distant galaxies, and also the beginning of the formation of galaxies and the formation of stars called the epoch of reionization. That's what it's called. There's a reason for that. It's a technical name, but just is where the first stuff is forming.
Yeah.
We haven't really seen that yet, and so the SKA will allow us to do that.
So we currently believe there to be billions. Is it correct? Billions of galaxies out there?
I would say trillions, actually, because I wrote a paper on that, but trillions, yeah.
Trillions?
Mm-hmm.
The size of the Milky Way?
No, a lot of them are much smaller. The Milky Way is quite a big galaxy compared to the average galaxy, actually.
So, for context, what's the size of an average galaxy?
The average size of a galaxy would probably be maybe 1,000, 10,000 times smaller than our galaxy, but in mass, not in size.
Okay.
So galaxies can change a lot in mass, how heavy they are, if you want to think of it that way. But in size, how big they are, the variation isn't so much.
So, when you say mass, do you mean what is within
like kilograms?
That? Yeah. So, like how many stars and planets are within that galaxy?
Dark matter.
If you were to put them dark matter, put them all into one big bag, that would weigh X amount. This galaxy would weigh X amount.
So it's not weight is a concept we have on Earth due to the gravity pressing down. But it's proportional. That is, it goes with the mass.
Right.
So your weight on the moon is different than your weight on Earth, but your mass is the same.
Yeah,
it's a fundamental unit of just how much matter you have.
Right. Okay. So if we're saying that the majority of galaxies out there are 1,000 to 10,000 times smaller than the Milky Way, for context, what would be the mass of the Milky Way?
Well, in astronomy, we like to measure galaxies' masses in units of the sun's mass.
Okay.
And so the Milky Way's mass is somewhere between, in exponential units, about 10 to the 11 to 10 to the 12.
Right.
Which is 10 with an exponent on top.
Yeah.
Masses of the sun. And that's about a trillion, I'm getting mixed up. A trillion solar masses, we call it. So
a trillion suns in the Milky Way.
Yeah, about that. Yeah.
Wow. And then, so in the Milky Way, we're looking at a trillion suns. So that's a billion suns. Is a billion a trillion?
Sorry, this is the American trillion. So this is 1,000 billion.
Okay.
Yeah.
Right. Let's run with that. That's easy for me to understand.
Yeah, 1,000 billion.
1,000 billion's a trillion.
Yeah.
Okay. Let's run with that. Okay. So 1,000. So lots of suns. Okay. We'll go about there. So, and in relation to what is a majority galaxy, how many solar masses would you say are in that? So you've got 10 to the 12 for the Milky Way. What would be the
10 million to 100 million, which sounds like a lot, but that's still, much less than
so massive.
1,000 billion. Yeah. But I should be clear that this is not the number of stars.
No, this is galaxies.
This is the number of, this is the mass this is the mass equivalent of a trillion suns.
Right.
So some of that mass is gas, a lot of it is dark matter, most of it is dark matter. And then you have lots of stars that are very low mass stars. So most of the mass of a galaxy is in low mass stars that are not like our sun. Our sun actually is, like our galaxy, quite a massive star compared to the average type of star that you have. Most of the stars in all galaxies are very small, low mass
in
stars.
comparison.
Yeah.
Okay. So with there being trillions of these galaxies out there, so you say trillions and multiples of trillions? 2 trillion.
Roughly, yeah.
And how do we know that?
This is something I worked on directly. So the way that we know that is that we now have very deep pictures of the very distant universe, and we think we can see galaxies almost back to the beginning. Now, we know we can't see all to the beginning, but we can see quite close to the beginning of the first galaxies. And these are very deep pictures taken with...
That was 15 billion years ago.
Well, 13.7, but around...
So that's the estimate, 13.7 billion, when they believe the Big Bang happened.
Exactly.
Right, okay.
Yeah.
So how long after that Big Bang can you see galaxies appearing?
Currently, we can see them about 500 million years after that.
Really?
But nothing before that. So there's a time...
That's still...
Yeah, it's pretty good, right?
Yeah.
But between beginning of the Big Bang and 500 million years, we have no observational information about the universe.
Wow.
So we don't know. And that's a very important time because that's when everything started really forming. But we don't have any data on that yet.
Do you think we ever will?
Oh, yes. This is what the SKA is going to do. And this is what the James Webb Space Telescope, something that I'm very involved with, will do as well. And this is going to be launched in December. It's a new space telescope, the successor to Hubble, and it will probe what we call the dark ages, that 500 million years that we don't know anything about.
Yeah.
The beginning of galaxies, the beginning of stars, the first structures to form. These telescopes will tell us about that epoch. So we really will. It's a very exciting time because this is the time in history that we will know what happened in the first hundreds of millions of years in our universe, and that's only going to happen once. And so in the next 5 years, we will have 5 to 10 years, we will have answers to these questions. Yeah.
And I think I've got a fairly good understanding of this, or I mean, for a YouTube researcher, but for people who don't sort of get this subject that much, would I be right? Would a fair explanation of these telescopes be that they are almost visual time machines, in that you are looking into the past due to the fact of how long it takes for light to travel through time from point A to point B? So it would take 10 billion light years for light to get to us, and that's what we're seeing from 10 billion years ago. Is that correct?
Absolutely correct, yes.
Yeah.
Mm-hmm.
Okay, good. Well done. Wow. So we're actually looking back to the very beginnings of what we believe created the universe. What do you believe created the universe? And do you believe there's more than one?
Yeah, those are big questions.
They're big
right?
questions. Big
Yeah.
questions on this show. It's a big question show.
So I wouldn't say I believe in any particular thing, but there are certain ideas that I think are worth considering.
Yeah.
Let's say. So there's the multi-universe idea, which is that there's some people think infinite number of universes,
Yeah.
and I think that's something that's worth considering.
Is there any evidence to suggest that?
No direct evidence, no.
Just theory.
But there are various things about our universe which we have theories about how our universe became the way it is that tell us there has to be other universes. So if that theory is true and it seems to work in our universe, then that theory says that there are other universes. And it's a very powerful prediction, but very hard to confirm because a distant universe is almost by definition not connected to ours. And so there's no obvious way to discover it or communicate or whatever you want to do.
Yeah.
Know it's there.
Yeah.
So it's a difficult problem, but many people who work on this take that very seriously and have developed many different ideas about it. So it's very, very popular. It's even comes about in quantum mechanics.
Yeah.
Quantum mechanics suggests there might be multiple universes as well. So it's not just cosmology.
So let's circle back a little further through time then. So we get to the point of creation of this universe. There was a Big Bang. And so explain what this, I mean, I know people are quite aware of the Big Bang theory that out of nothing, all of a sudden came something and there was a huge explosion that created everything that we have, and it's why everything is still accelerating from this original explosion 13.7 billion years ago. Right. Is that a fair sort of primary school reflection on
More or less, yeah.
Right.
I think some people would say that it's not something from nothing, but that everything was at the same kind of location or the same.
So all of the universe's mass was pulled together into one point.
You can think of it like that, yeah.
And then it suddenly went. So what? So there was. Okay. So what I'm trying to understand is if everything that's in this universe existed in one place 13 billion years ago. Is that the theory?
Yeah. That's right.
And what was that one big giant star?
No, it was much smaller than a star. I mean, it's infinitesimally small location in space where the laws of physics that we know don't work.
Right.
That's the basic idea, and we don't really know anything about what happened. If you want to think of something before that, what happened before that, or the exact
is there any
reason
scientific
that it happened.
Theory around? I mean, obviously the immediate thought is to go to some kind of creator, or it's where you get onto more spiritual concepts, I suppose. But without going to a spiritual concept or looking at God or anything like that, is there anything that science could suggest was there beforehand to instigate this Big Bang?
There's no evidence for anything. More or less. There are some people who claim they see something, but it's very controversial.
Right.
In terms of
see something as in what?
Well, you have what's called the cosmic background radiation. Have you heard of this? This is a light, the first light in the universe, which formed when protons and electrons combined.
Yeah.
And when that happens, they emit light.
Yeah.
So that was the first time the universe was cool enough such that electrons and protons could combine to atoms, the first atoms, hydrogen, essentially. When that happens, you get the release of energy, and that is light. And we can see that light, and that's called the cosmic background radiation. And that happened about 300,000 years after the Big Bang.
Okay. That's relatively, well, that's
pretty soon afterwards in terms of a cosmic scale, right?
Yeah, it's like the next day.
We can see that, but after that, we don't know what happened. This goes back to the Dark Ages until 500 million years when we can see things with Hubble.
Right.
So some people, going back to your question, some people think they see structure in that light, that early light, which would suggest that there was a previous universe. So that's one idea, is
Okay.
that the universe expands and then contracts and
Expands and contracts.
then continues. This is a cyclic universe.
Yeah.
And there are sophisticated theories that have been written down about that and how
Yeah.
that works. And there's even popular books written about it.
Yeah.
So some people think that that's a possibility, that it just is a cyclic thing, that it keeps going.
Yeah.
But then you could ask, well, what started that? I mean, has that been around forever? And
Yeah.
and if it has been around forever,
Then what
you know,
started
why has it been around forever? How
Yeah.
can something be around forever? What does that mean, forever? So
Yeah. Forever.
every question that you answer comes up with a more difficult question.
Yeah.
So
What I've all found fascinating, but mind-boggling, is the size of the universe. I mean, we think of the Earth. I mean, from our perspective, flying from, for example, Manchester to LA, we think of that as some sort of distance.
yeah.
We think of the Earth to the moon, 250,000 miles, whatever it is, some kind of distance. But this is nothing. This is absolutely nothing. Even the Earth to the sun is 8 minutes worth of light, right? Something
Right,
like that.
yeah.
It's nothing on a cosmic scale.
Nothing. Yeah.
And when you start thinking about, 1,000,000,000 light years away, that's 1,000,000,000 years of light traveling at the speed of light
Yeah.
to reach a certain point. I just
Exactly.
find that just an immeasurable amount of distance.
I agree. Yeah. It's funny that when you work in this area, though, you sort of
Detached.
you don't think. Yeah, exactly. You don't think about these things in such a philosophical way. You just sort of accept it as
as
it is,
mathematics
what it
and
is.
science.
Yeah, and you just kind of treat the objects, even if you're looking at a galaxy like I do, which is, the light left 13 and a half or 13.2 billion years ago. That
Is that one you're studying at the moment?
Yeah. That's right.
So when you are receiving information and data on that particular galaxy, is that just coming to you in, because it won't be images, surely?
No, it is images.
It's actual
That's
physical
often-
images.
That's often, how we see them.
Wow. And what is there a difference in physicality to what image galaxies look like from back then to newer galaxies today?
Yeah. So this actually is a topic that I study a lot. So
Okay.
I know a lot about this. Now, when I say images, you might think you see this brilliant big picture of a galaxy like
Like
that on the wall.
Yeah.
But that's not how it is. It's
Okay.
often just a tiny blob of light
Right.
that has no structure at all. And this is almost always, but not always, but almost always from the Hubble Space Telescope, which
Yeah.
can take the deepest imaging that we can do right now.
Yeah.
And so you see these things and you can see them in pictures. That's the easiest way to see them. Or images, pictures. I use the word interchangeably. It's not quite a picture. These images, and you have to figure out how far away they are. It's not like you take a picture of it and you go, oh yeah, I can see already by eye that it's at,
Yeah.
this early universe. You have to analyze the galaxy to determine that it actually is that distance away. And that takes some effort. And there's some uncertainty in that process as well. So this is a hard thing to do. So some galaxies that we think are at the edge of the universe actually are a little bit closer. Closer being like, 5 billion years. 5 billion light years away, which is still really far. But for people who study galaxies at the early universe, that's really not that far.
Right. And so when you receive a blob of light you get sent this digital image, I imagine,
Yeah.
lands in your email, blah, blah, oh, we found a new galaxy, it's from the beginning of time, and it's a little blob of light. What's the process then? Do you then look at how the light is splashing around, or like how do you differentiate one blob of light from another?
So yeah, you asked another question, which I'll come back to. So the blob of light, you can determine how far away it is because sometimes you can take what's called a spectrum of it, which is like you disperse the light of the galaxy into like a rainbow. Think of it that way.
Yeah.
And sometimes galaxies, even at these distances, will have what we call emission lines.
Okay.
And these are very identifiable lines of emission that come from just hot gas in the galaxy.
Right.
And so if you see an emission line in the spectrum of a galaxy,
Yeah.
and you know what is the wavelength of that light, then you can figure out how far away the galaxy is. The
Right.
reason being is because the universe is expanding, right?
Right.
We all know this. in astronomy.
Is that official or is that a theory?
I think it's pretty much official now.
Right.
Yeah, there'd be very few people who would disagree with that.
Right.
That the universe is expanding.
At what rate?
Well, it depends on when you're looking. But if you're looking today, the rate is known as the Hubble constant, which you may have heard of.
Yeah.
And that tells you how fast space is expanding, given a distance between galaxies. And the number is around 70 kilometers per second per megaparsec, which is the technical unit. So
70 kilometers per second.
for every megaparsec. So the nearest galaxies are about a megaparsec away, maybe a little closer. So
What's that
for
in
every
linear
70,
terms?
sorry?
What's a parsec in linear terms like?
It's 3.18 times 10 to the 18 centimeters, I think. Although
Centimeters.
yeah, I know. We use centimeters in astronomy. I don't know why.
They use centimeters in astronomy.
Yeah.
Why?
Actually, I was debating this with a student today. I don't know why.
Just like, let's make this
Yeah.
more complicated.
In physics, we used kilometers, which would be more. But in astronomy,
Yeah.
we use centimeters.
I mean, kilometers or miles would be. I mean, I'd say kilometers because at least it's a
well,
metric.
yeah, you want to stay on metric.
Yeah, miles doesn't make any sense. But
Yeah.
centimeters.
Yeah,
Good God,
it's crazy. Yeah.
that's. I mean, yeah. You might as well do millimeters.
Yeah.
Wow. So, how many kilometers to the nearest galaxy would you say?
Kilometers to the nearest galaxy. Oh boy, this is a real quiz here. So the nearest galaxy is, well, it depends on what you mean by nearest galaxy. There's galaxies falling into our galaxy.
Okay.
So in some sense, they're just approaching.
Due to the expansion.
So the thing is about the nearest galaxies is
Yeah.
that they aren't expanding away from us because they're attracted by gravity
To us.
to us. So they stay
Because we're bigger than them.
bound to us.
Right.
Yeah. And so you have to go kind of further away to see the expansion
Right.
of the universe, of galaxies going away from us.
Right.
But the nearest galaxies are about, I don't know, 250,000 parsecs away. And a parsec is about a couple light years, so it would be maybe about 1 million light years.
And that's the closest one.
Roughly about that, yeah. Yeah.
1 million light years.
Maybe a little less than that, but around there, yeah.
That's relatively close, I suppose. In cosmic
Well,
terms.
when you're talking about 10 billion, yeah.
But the thing is, we don't actually know if they still exist. What we see from 1 million light years ago.
Well, I mean, yeah,
that
I've
would've
heard
been
that
a-
before, but it's true to some extent that you don't know for sure.
Mm-hmm.
So, but if you just look at scientifically, how could you make a galaxy vanish
Yeah.
in
Does
a million
time even
years?
become relevant in this once you get to this sort of level of thinking?
It does, but only on very large scales.
That's what I mean. But because we consider time in our 3D 9 to 5 world as something quite important. But on this kind of scale where you're talking about, massive, gigantic distances with massive objects and that are incomprehensible, on an Earth scale.
Yeah.
It's actually you can't compare the two sort of.
Yeah.
The scales are completely out of sync with each other. So what I'm sort of getting at, does time become irrelevant almost? So when we're saying something's 1 million light years away, we're talking light years around 365 days around the sun.
Yeah.
So we can understand it.
Yeah.
But really, from a universal perspective, I suppose that wouldn't make any sense.
Very short time scales like that make little sense on the scale of galaxies.
Yeah.
But if you're talking about like 500 million years or 1 billion years,
Yeah.
a lot can change
Right, okay.
in that time. So it's just because it's so large. Now,
Yeah.
now I should say that's not true for all parts of galaxies. In the very centers of galaxies, you have massive black holes, and the regions around those black holes is very small. And so you can see variability, we call variability, changes in the light coming from the centers of galaxies on scales of days, sometimes hours. You can see changes in the very centers of galaxies,
Right.
where you have a very massive black hole. So if you look at a galaxy, the whole galaxy won't change over, millions of years.
Yeah.
But the center of the galaxy can change very rapidly, on the order of, like I said, days or weeks.
Days or weeks?
Yeah, months. Yeah.
Really?
Yeah.
Wow. Why does I know I'm quizzing you like a child here, but I'm finding it fascinating. So, why does every galaxy have a black hole at the center of it?
Well, that's one of the big questions in galaxies, is why that's the case. And there is no
Do you have a theory?
obvious answer. Well, if you think about how galaxies are forming, they form initially from gas just collapsing.
Yeah.
And when gas collapses, you might think that in the very densest part in the center, some of that gas collapses to the point where it's forming a black hole.
Right.
So that's one idea. And then you have galaxies growing with time, and they grow with time by accreting other galaxies, by accreting gas,
Yeah.
which just surrounds galaxies, because there's gas between galaxies. There's lots
Yeah.
of gas between galaxies. And that gas can fall into the galaxy. And some of the gas can go right to the center of the galaxy, and then it can feed that little black hole, which may have formed in the beginning when the galaxy first collapsed.
Mm-hmm.
And then you get, over time, a growing black hole in the center that is growing along with the galaxy. Because we find that the weird thing about it is that the mass of that black hole in the center is highly correlated. That is, if it grows, the mass of the galaxy also grows, such that the relation is very good. That if you have a massive black hole in the center, you have a massive galaxy. It's not random.
Right.
And how that can develop is something that is still a mystery. So people still talk about this a lot.
What exactly is a black hole? If you were to explain it to someone who didn't know.
Yeah, good question. So a black hole, really, in its simplest terms, is just something which has enough mass that it has a event horizon, which is a really bad movie, but also
I loved it.
I'm just kidding. It's a great movie. That the event horizon is essentially where, if you go beyond it, when I say you, I mean anything,
Yeah.
including light, that it cannot escape. That the escape velocity, that is the velocity needed to escape the gravity of the black hole, is higher than the speed of light. And if you have a velocity higher than, if you have escape velocity higher than speed of light, then nothing can get out of the black hole. So that's the most general definition of a black hole.
And where does it go?
Where does what go?
The light
It stays within the system of the
within the mass.
black hole. Yeah.
So they don't know what's through it. Well, would there ever be? I suppose there would never be a way of ever finding out what's beyond that event horizon, because radio signals or light would never be able to come back to the receiver.
Not directly, no. I mean, you have some ideas from Stephen Hawking about black holes can evaporate. You have things like Hawking radiation,
Yeah.
again from Stephen Hawking, where you have virtual particles near the event horizon, and
Yeah.
the virtual particles are where you have
Virtual particles.
yeah. So throughout space, at all times, you have virtual particles forming very rapidly and then disappearing. It has to do with the uncertainty principle,
Yeah.
quantum mechanics, where you can have a certain amount of energy within a certain amount of time,
Yeah.
but these things are very small. And so you have like a particle and its anti-particle forming, and then they basically recombine and vanish. But if it's near the black hole, the black hole can sort of take one away but leave the other, so they can't sort of disappear because they can't annihilate each other.
Yeah.
This is a basic explanation of what Hawking radiation is. And so that and evaporating black holes are some of the ways that you can perhaps learn
More about them and what's beyond them.
That's right. And there's also ideas that black holes, sometimes it's said that black holes, they have the same properties. The no hair theorem, I think it's called, where you have black holes, they essentially are in many ways identical.
Right.
That it doesn't really matter how they got there or their history, but if we're given for the same mass, so they have different masses, that's for sure.
Yeah.
So black holes can have a variety of masses. There's no question about that.
Right.
But beyond that, and maybe a couple other basic features of a black hole, that they're more or less identical. This is again a theorem.
So how long have you worked in this field for?
Well, let's say about 20 years or so. Yeah.
Okay. So in 20 years of working in astronomy and cosmology,
Yeah.
would you say, in your experience, is it all random chaos, or is there patterns to it?
Oh, there's certainly patterns, definitely. It's all patterns, more or less. Except when you go on the very small scale, when you go to quantum level. There it's, I wouldn't call it chaos, but it's more of a randomness that you can't predict,
Right.
which is the whole idea of quantum mechanics.
But everything out, but from a non-quantum perspective, it's easier to predict. There's a lot of patterns.
There are many patterns in science. Yeah.
Would you, in your experience, would you say that evidence points towards an intelligent design of the universe?
I would say no in a traditional sense.
In a traditional religious sense, perhaps,
I would say no, probably not. No.
What do you mean by a traditional sense, though?
A traditional sense of intelligent design is that everything is put into place by an intelligence and is designed that way.
Yeah.
Like we are designed by, God or whomever,
Yeah.
and that's why we are the way we are.
Yeah.
So I think very few scientists would think that. Even religious scientists
Yeah.
wouldn't believe that.
Yeah.
And that's the case. That that we didn't come from a somewhat random evolutionary process from early, life on Earth.
Yeah. Yeah.
And I say semi-random because, evolution is random in a sense that you have a randomness change in genetics and genes, which can produce advantages. But the fact that we have intelligence, the fact that, certain animals have distinct abilities that make them survive better, like wings or eyes or, hands and whatever, that's not necessarily random because that is an advantage. And so eventually you could think over billions of years that these kind of advantages would appear in some form.
Right.
So, but the process itself, the day-to-day process is random, but the net result is not so much.
Right. Okay. So you would say that the evidence from an astronomy perspective would say that. So what do you have any spiritual ideas on how this all started?
The universe itself. No, really, no. I wish I did.
So you've never thought like, this place is so massive. This is so much going on here that's so incredibly difficult to understand and figure out. How did it all get here? Do you know what I mean?
Yeah, I do. It's a good question, and I have thought about it, but I certainly don't have
an idea.
Well,
I don't expect you to have the answer.
Good guess or an answer.
You wouldn't be on this show if
Yeah,
you had
right.
the answer to that.
I'd be somewhere else right now.
Yeah, you would. Yeah.
Wouldn't be drinking tea. I'd be drinking
You'd be
champagne.
Yeah, you'd be drinking something a lot better than tea. Yeah,
Well, that's good tea. Thank you very much for that.
But this is what I find. Like, I think what attracts me, and I think a lot of people to the concepts around space and astronomy and cosmology is the mystery of it, and it is such. I mean, it's so beautiful out there, but it's so insanely hard to comprehend exactly what it is that's up there, and down there, and left and and right of us, which I think is. Yeah, I think.
You mean the ultimate origin of it all?
Yeah, I mean.
Or like the why questions.
Yeah, there's the why question. I think it's the why questions, really. I mean, just for example, going back to the beginning of the conversation, we spoke about 1 trillion 2 trillion galaxies.
Yeah.
2 trillion galaxies. Now, for me, that's just knowing that there's about 1 billion stars in each galaxy.
On average, yeah.
On average.
Something like that.
I mean, that's just a phenomenal amount of matter. And then there's antimatter or dark matter, whatever it is, which I don't understand what that is.
Antimatter?
Dark matter.
Oh, dark matter. Yeah, that's a whole other.
Does
topic.
anyone understand what it is?
We know quite a bit about dark matter. Yeah.
Is it physical? Could you
Many
drive?
people think it is. Yes.
So you could drive into it and crash.
If it was dense enough, yes, sure.
And does it have planets, galaxies within it that are dark galaxies, dark planets?
We don't know for sure how it's structured.
Right.
If that's what you mean. It could be diffuse or it could be structured, and some people think it's black holes that are very small, black holes that formed in the early universe. That could be a dark matter. Other people think it's it's like a diffuse sort of thing, like gas.
Right.
It follows gas often in galaxies. But in terms of the particle of what is made of, we don't know that. That's
Really?
really what people want to know, is what is the particle that it's made of? Is it the black holes, or is it some exotic particle that we just haven't discovered yet? And there's many theories about what that particle could be.
And it doesn't emit light, does it?
No, that's the definition of it, yeah.
So there's no way of knowing really how much of it exists.
No, we know a lot about how much of it exists. That's one thing we do know.
How do we know that though?
Because we can measure the masses of galaxies. We can measure almost, in a sense, the mass of the universe.
Yeah.
And we know how much mass it has, and we also know how much mass that we can see.
Yeah.
And so we can say easily that, okay, well, we know how much mass there is that we can see with our eyes, with our telescopes. Mm-hmm. But our measurements are telling us that there's a lot more mass there.
Right, okay.
So that's the idea. So dark matter really should be called invisible matter.
Right.
It's not dark. It's not black or something. It's like a dark cloud. It's invisible. So if it was in this room,
sounds more
wouldn't.
sinister, doesn't it, when it's called dark matter? It sounds like, the dark matter that we can't see that's planning and plotting against us. Yeah. But it's essentially, it's just
invisible.
Invisible matter. Invisible to what we know, essentially.
It's invisible to electromagnetic radiation.
Right.
Which is, any kind of light emission, like
just the
visible
opposite.
light that we can see.
It's the opposite of light.
Well, it doesn't emit light. I wouldn't call it the opposite of light, but it doesn't emit light. So it's the opposite of something which emits light.
Right.
In the sense that it doesn't emit light.
It doesn't reflect it either.
No. Light just doesn't notice it. It goes right through it. Doesn't bounce off of it. Doesn't.
So it goes right through it.
Yeah. Mm-hmm.
That's crazy. So even if it was dense enough to be physical, light would still go through it.
Yes.
That's insane.
Yeah, it's pretty cool.
And what percentage of the universe do we believe to be dark matter?
Well, it depends on what you mean by that. So we think the universe, and this is another topic, is around 70% dark energy, which is something completely different. And then the rest is mass.
Right.
And then about 1/5 of that mass is stuff that we know.
So what's dark energy?
So dark energy is just as mysterious, and the dark energy is you can think of it as the pressure which makes the universe accelerate.
Right.
So the universe, we talked about it, is expanding.
Yeah.
But the weird thing about the universe is that it's not only just expanding, that expansion rate is going faster.
Right.
So over time, it's going faster and faster and faster.
Okay.
So
that is the
why
pressure
is it doing that?
From its original explosion.
No, it's not. Not necessarily.
Oh, really?
Yeah, because the original explosion, if you just explode something like the universe, then it would expand, but it has lots of matter in the universe as well.
Yeah.
And the matter would eventually start attracting it to itself, and the expansion would slow down, and then it would, if it's enough mass, contract again.
Yeah.
But what's happening is that even with this matter, the universe is expanding from the Big Bang, but it's accelerating even faster, even though there's this mass which is attracting itself, that it wants to go back. The mass wants
to go
the
back,
Big Bang
but something else
to slow down.
is
But
keeping it going.
it's expanding. In fact, for decades, astronomers were looking for the de-acceleration, the slowing down of the universe. They thought it was slowing down because you have all this mass. The universe must be slowing down because all the mass is attracting each other.
But they
So
actually found the opposite.
they found the opposite. And this is why I won a Nobel Prize, because it was such a big discovery.
Wow. So God, what are the implications for that? That's insane. So it's exploded, and then something's gone, hang on a minute, let's keep going.
Yeah.
So it's almost...
Yeah. There's a lot of theories about it. The basic idea is that space itself is doing it. And space you make more space and it produces a sort of this pressure,
Right.
which is pushing out. That's sort of a general one idea of how this works.
But there's no evidence for anything as of yet. but technology is improving, so we're thinking the next 5 or 10 years we're going to get answers to some of these questions.
Yeah, there's many projects going on now to answer the question of the details of how the dark energy is changing, and that'll give us some better idea of what is the origin.
Yeah. And funnily, you're the first person who works with space, should I say, who I've not even mentioned aliens to.
Yeah, I was gonna say, we haven't even talked about aliens
yet.
Yeah.
Have you've seen the Pentagon release papers, I'm guessing?
Yeah.
What do you make of that?
Interesting stuff. Yeah. I don't think it's aliens.
What do you think it is?
I think it's a mixture of just strange optical effects and.
But it's physical. It's physical objects that are about.
No, I know, but some of
30
it
feet
is
wide.
the way you can interpret it, the way you can see it. Not all of it, and some of it might be things that you know, the way that light and water and different scenarios can interact together. That maybe it's in ways that we haven't seen before.
But that wouldn't create a physical object. That'd create a mirage.
Wouldn't create physical objects, no.
But they're giving off heat.
But you can see something that can look like a mirage or something that could look like a physical object.
I think I totally agree with you on that. I think
that's what I mean. Yeah.
I think the sightings I'd just put them in the bin. So you can't say there's anything there's no evidence around it. Yeah. But what's strange is the ones that giving off heat signature. And they've measured them. They're like 30 feet. They're saying the same size as like an F-14 or something, and they're pulling maneuvers that would destroy a human being within like the G-force alone.
I think you know more about these than I do, to be honest.
Yeah.
Yeah,
look into it.
Certainly worth looking into.
I'd look at honestly, Chris. It is, and I'm not saying this to sound like a UFO nut because I'm not a UFO nut, but I do find this stuff beyond. It's strange to say the least.
Yeah.
And the fact that the Pentagon are releasing it to us, I think is. I
mean, you're a good example of this. Is that people, humans, are really interested in this topic.
Yeah.
And extremely interested in this topic.
Yeah, it's contagious.
Yeah. And so as a astronomer scientist, I think that we should, not only just be aware of that, but should discuss these things and try to explain them as much as we can.
Yeah.
And to hopefully, for me, get people interested in other areas of astronomy through
people having an interest in
what's happening in the universe itself. Aliens is
one part of it.
It's probably part of that in some ways.
What was interesting is that when I spoke to Eamon about this, I did quiz him on aliens.
I saw that. Yeah.
Quite a lot. But what he said, which really sort of made quite a lot of sense to me, was that even though life on other planets is definite, almost, it's guaranteed, it's still so rare on a cosmic scale.
Yeah.
So the odds on it are almost guaranteed because there's so many planets, so many stars that.
Yeah. The issue with this is the lifetime of a civilization. So, let me back up a bit. There's two things. One is life itself, and the other one is intelligent life like us that can communicate and has technology.
Yeah.
Those are two different things. So life, just basic life, is probably not that uncommon. I would guess.
Microbial life. Yeah. That's probably quite common.
It's probably quite common. But really intelligent life, it's, aliens, what we're just talking about, things that people really want to know about. Yeah. Let's be honest, that's what people want to see. They want to see, other intelligent creatures that, have, a super iPhone or whatever. Right? They want to know what's going on.
Yeah.
And that is really difficult because of the lifetime of civilization. The lifetime of these civilizations is probably not very long.
Yeah. Long enough to get here.
Well, maybe not. I mean,
because if you think
the stars are really far away, and you would,
even the close ones, from a physical life perspective, lifetime perspective, 100 years we live for, say, you'd have to have intergenerational, well, linear travel is definitely not possible. Because if you're traveling at any sort of speed, the tiniest little rock's going to destroy the ship. Or even if you got around that, the radiation, whatnot, everyone will have cancer by year 5.
There's all kinds of technical problems. Yeah.
You'd never get there. So that's not going to happen. There has to be another way. And if there isn't another, or maybe we're just not designed to meet other life in the universe. We're designed to exist in our own world, and that's that. Because it does seem, unless the, like in that film Event Horizon that you like, your favorite film.
Is it on Netflix?
It is actually. Yeah.
Is it? Okay.
Where they bend space time, and if that, I know that's a theory. Yeah, I don't know if that's been proven to be possible at some point, but.
Well, there are many ideas about that. Well, but one way of looking at this is what's called the Fermi Paradox.
Yeah.
Have you heard of this?
No.
So the Fermi Paradox. So Enrico Fermi was a famous physicist who won the Nobel Prize, and he was one of the people who invented the atomic bomb. But anyway, one of the things that he did was he asked, well, if there are aliens throughout the galaxy universe,
where are they?
Where are they? Why haven't we seen them?
Yeah.
And that's really a profound question. And if you think about it this way, our galaxy has existed since beginning of time, more or less. But you can see stars that are old as the Big Bang, more or less. Yeah. And so there's been stars in our galaxy for that long. Our sun, though, is only 5 billion years old.
Yeah.
So the galaxy has existed for 8.7 roughly billion years before our sun even existed.
Yeah.
And then it took 5 billion years for us humans to exist.
Yeah.
That's a lot of time.
Yeah.
And there's a lot of stars in our galaxy. Yeah. So if even one of those stars had developed a life and developed, human-like, intelligent life, 5 billion years ago, 1 billion years ago, 100 million years ago, whatever, million years ago even.
Yeah.
And if that life developed the same way that ours has, intelligent life, where we're getting better and better technology at a huge rapid rate. I mean, look at where we were 200 years ago.
We're pumping out signals into space constantly.
Yeah. So think about how much technology we would have in 1,000 years. Think about how much technology we would have in 10,000, 1 million years.
Yeah.
It's unbelievable what we could do. So if something like us had existed back then they certainly
we should have
we would see something
or detected a signal.
So it's a bad sign because it means that if either they never existed or they did exist, but they're gone now.
Yeah.
So that tells you that the lifetime, because we don't see them, that the lifetime of these civilizations probably isn't very long.
Yeah.
And you can understand. I mean, you look on Earth,
look at us, we've not
look
got
at all
long.
the ways that we're destroying the planet, each other.
It's almost impossible to think that humans will be around in 1 million years.
Sadly, I would agree. Yeah. But the thing is that, and I thought about this a little bit, is that if you get enough technology, even maybe 1,000 years from now, you could create robots that could go into space and could carry on your civilization, not with you as individuals, but at least your technology, your culture in a sense.
Is AI could continue.
Yeah, exactly.
Yeah.
But we probably would have seen that too. So that tells you again that lifetime of intelligent civilizations probably isn't very long. But the caveat is that maybe they found a way that we just can't see it, right? That's always what someone
maybe it's in the dark matter.
Yeah, maybe it's dark matter. Yeah, probably not though.
Yeah.
That would be strange.
Yeah, it's such a massive subject, this, and I feel like in like the 40 minutes that we've been talking, we've kind of like, it's been like we've touched on every part of like astronomy, and but it's I love these conversations because it's so eye-opening, and I think more people need to invest in this subject, like need to spend time and look into it. And I think there should be, I think it's a fascinating subject that I think it can only open people's minds more. And I think ultimately, once you start seeing the size of this universe and the size of these galaxies out there, it makes you realize how insignificant and small we are, and maybe we shouldn't just be all warring and fighting and killing each other and having such petty divides over religious, political, economical, whatever concepts that we all find ourselves struggling and messing around with every day.
Definitely, yeah.
Well, thank you very much, Chris. It's been brilliant, mate.
My pleasure. Thank you.